Hello, my name is Kevin. In this opportunity, I would like to show you my research on developing an atomic force microscope setup to measure the mechanical properties of biofilm. First off, you might be wondering why do we need to measure the mechanical properties of biofilm in the first place? Before we get into the research experiment and data, I would like to introduce you to the core of the problem. Bacteria are ubiquitous, meaning that they are everywhere. Although most are harmless, some causes infections and diseases. For example, E. coli, commonly found in foods and intestines, it is one of the leading causes of common diseases and food spoilage. One of the common diseases caused by E. coli is diarrhea. Diarrheal diseases account for 1 in 9 child deaths worldwide, making diarrhea the second leading cause of death among children under the age of 5. Thus, we need to come up with a strategy to eliminate pathogens, or known as bacteria, that causes detrimental health effects. There are many methods to eliminate pathogen in food, such as inactivation using chemical agents, thermal treatment, and ultrasonication. However, such methods usually decrease the nutritional value in food. The ultrasonication method is one of the popular methods to preserve nutrition in food and as well as maintaining the flavor and texture. Here in this image, we can see the working principle of ultrasonication. Basically, it utilizes the concept of cavitation. The popping bubbles in the ultrasonication method releases high pressure that destroys bacteria. Most ultrasonic devices on the market usually operates on a single frequency. Thus, our lab has successfully designed and prototyped an ultrasonicator device that operates on multiple frequencies to inactivate bacteria. The result shows that the ultrasonicator is capable of eliminating bacteria colonies down 3 orders of magnitude after 15 minutes of treatment for E. coli. As you can see on the graph, the first 3 minutes, the line goes down rapidly down to 1 to 2 order of magnitude, or 2 order of magnitude for all samples, and up to 15 minutes of treatment for E. coli, our device is capable of reducing the bacteria colonies down to 99.9%. Although the result is great, we believe we can do better and improve our device. To improve the ultrasonicator, we need to study the behavior of bacteria under stress. Thus, we conducted a study to examine the bacteria breakdown process. The study is conducted using Abacus, a finite element analysis software. The rod-shaped model is E. coli, while the sphere-shaped model is Bacillus subtilis. As you can see in these images, the picture in grayscale are the real-life bacteria, and the picture in color is obviously the simulation model. The breakdown in the simulation resembles perfectly to the real-life condition, proving our lab success on simulating the breakdown process. Here are the videos of the simulation. And here are the breakdown process of Bacillus subtilis. The perforating models tend to have a hole on the bacteria during the breakdown process, whereas the bursting models have this rupturing effect during the breakdown. The simulation is still based on multiple assumptions, and the mechanical properties used in the simulation are obtained from secondary data. To improve the accuracy of the simulation, we need to measure the mechanical properties of bacteria. Out of several popular methods to measure the mechanical properties of a singular cell, AFM stands out to be the best option. It is non-destructive and does not interfere with cell physiology. It's capable of measuring forces down to piconewton level. It's capable of measuring all kinds of deformations in all types of cells and able to characterize the heterogeneities of tissue in single cells within the submicron level. Despite the name atomic force microscopy, which sounds kind of sophisticated, the mechanism is actually really simple. First, we have this cantilever beam straight with a length of L. Then we point a laser on the reflector of the cantilever. The laser is reflected and received by a photodetector. This photodetector basically reads the position of the laser spot. Say we have a force on the edge of our cantilever. The cantilever bends, which also changes the angle of reflected laser. The change in position on the photodetector is what we call delta PSD. The length of the reflected laser path is denoted by D, and the deflection of beam at the length of L is denoted by ZC. This method is what we call the optical lever method, which basically measures force interpreting the change in laser position. Here are the equations that we use to calculate the force. Here is our experiment setup. First, we have our linear stage. It basically moves our cantilever and our sample in 3 different axes by turning the knob on the stage. Zoom in. We have our cantilever. Then we have a laser pointer here and a magnifier here. Since our AFM cantilever is so small, we need a magnifier to reduce the size of the laser by focusing it. When you shoot laser on the AFM cantilever, it will look like this. It has a small red light on the edge of the cantilever. Then the laser will be reflected into the photodetector, which reads the changes in the laser position. Then digital microscope here records the entire measurement process. In this experiment, we also included another cantilever for comparison. Cantilever A is manufactured by a company called Budget Sensors, and cantilever B is fabricated by our lab. The measurement of the biofilm can be seen in this video. The right side object that looks like a tongue in our biofilm, it's a kombucha biofilm, one of the most researched biofilms in literature. We chose this as our biofilm since it's easy to produce and it already has a lot of research on it. To obtain the mechanical properties of bacteria, we need a contact model. There are various contact models. Hertz model, the same person who discovered radio waves and the same person behind the frequency unit. Hertz was the first person to create a contact mechanics model. Basically, he started the contact mechanics field and he created a contact model that describes the localized stress from non-conforming contact between 2 curved surfaces that deform slightly under applied load. In his contact mechanics model, he assumed that the deformation was elastic and there was no external forces such as intermolecular force nor adhesive force. When we look at the left picture, imagine that there's 2 curved surfaces coming into contact with each other. Both surfaces are non-conforming, meaning that they don't fit for each other, and they are forcing their way into contact. As the load is continuous, they deform and squeeze into a flat plane, as shown as in the picture on the right. And the picture on the right is basically a close-up look on how 2 curved surfaces come into contact when they are elastic. They tend to be flattened by each other. Now here is the equation. The equation on the right describes the contact force between two bodies. This equation that contains the subscript E is the effective elastic modulus. It's basically the combined elastic modulus of two objects coming into contact subjected to normal force. Then we have Snedden's contact mechanics model. Basically, almost all mechanics models are derived from Hertz's contact mechanics model, so all of them share the same limitations and assumptions. In this case, the difference between the previous model is that this model is a rigid cone, and it leaves an indentation on the opposite surface. Snedden created this model to include more axisymmetric geometries. The equation on the right is the contact force between a cone and a flat surface. Usually in the field of contact mechanics and AFM, a four-sided pyramid is often approximated as a cone by researchers. Although the result may be close, it still yield errors. Thus, a group of scientists developed Snedden's model into an ideal four-sided pyramidal indenter. The mechanism is the same as the previous two models. When analyzing the contact, we realized that there are many possibilities of the contact mode. We divided the contact into three cases. Case 1 is where the indentation depth is based on the difference between the cantilever and sample stage position. And case 2, which is the hypothetical case, is when the indentation depth is based on the AFM tip overall height, which is around 12 microns. And for the hypothetical case 3, the indentation depth is based on AFM tip effective height, which is around 800 nanometer. Due to the limitations of the study, we decided to measure only the elasticity of the bacteria. Here is the final equation used to measure the elastic modulus of a cell. Rico's and his colleagues' model is chosen due to the shape of the probe. The E subscript is the effective elastic modulus, meaning that is the combined elastic modulus between two surfaces. This E bacteria is the parameter that we want to calculate, and the force here is obtained through optical lever method using the photodetector sensor. Here is the indentation depth that we mentioned before, and this alpha sign is the half cone angle of AFM tip specified by the manufacturer. For the data and analysis, we will be comparing the experiment values to three commonly found microorganisms in kombucha biofilm. We will be comparing to Comogetia bacter salinus, Schizosaccharomyces pombi, and Saccharomyces cerevisiae. And in terms of order of magnitude, both case 2 and case 3 resemble similar values to Comogetia bacter salinus reference values, with a difference of 1 to 2 order of magnitude. Case 1 here, the average value deviates greatly from the reference values by 3 order of magnitudes when compared to the compressive testing. The compressive testing is the first 2 bar here that you see on this slide. Let me draw it for you. This value is obtained using compressive testing, and this value is obtained using tensile testing. As I mentioned before, case 1 here, it deviates from the reference values by 3 order of magnitudes when compared to the compressive testing, and 5 order of magnitude when compared to the tensile testing. Case 2, on average, deviates by only 1 order of magnitude when compared to the compressive testing, and 3 order of magnitudes when compared to the tensile testing. Similarly, case 3 also deviates by only 1 order of magnitude compared to the compressive testing, and however, for the tensile testing, it deviates by 2 order of magnitude. Schizosaccharomyces pombi is another common microorganism found in kombucha. When compared to the reference values, Case 3 yields the closest values on average, this time with a shy difference of 2 orders of magnitude. Case 1 here deviates significantly by 6 orders of magnitude, while case 2 deviates around 4 orders of magnitude. When compared to the Saccharomyces cerevisiae, all of the experiment values deviates greatly from the reference values. Case 1 deviates by 8 order of magnitudes, case 2 deviates around 6, and case 3 deviates around 4. What does this tell us? The AFM setup has been successfully assembled. Successfully as in it has proven its orbital functionality as a proof of concept. On average, case 3 resembles the reference data the most in terms of order of magnitude when compared to the reference values, and the bacteria contained in the Kombucha biofilm are most likely to be Schizosaccharomyces bombi and Communautaria sanans. As for future work, here are the suggestions from me. First, the linear stages be replaced with a motorized computer-controlled stage. A piezoelectric force transducer should be included in the experimental setup. The experimental setup should include a dedicated platform with the tap holes for the equipment to fasten. Future work should consider the intermolecular traction, adhesive, and frictional forces between contacting surfaces. And the laser should be replaced with a helium neon laser since it is more stable, smaller in size, and has a high quality optical output. And before I end the presentation, I would like to explain the purpose of our experiment. Here is our research framework. First, we measure the mechanical properties of bacteria using AFM. Then we use the data obtained as a parameter for the simulation. After studying the bacteria breakdown behavior, we can use this to improve the ultrasonicator. Then the ultrasonicator will yield results where the examined values are the bacteria eliminated in terms of order of magnitude. All of this process is an optimization to the ultrasonic device. And that is all from me. Thank you very much for your time. And may you have any questions, please email me.